Hi, this is Andrea Hendricks, and today's lesson is going to be on solving systems of linear equations by graphing. To be successful in this section, you must know how to graph a linear equation, and we've discussed this already with two different methods. In some cases, you're given the standard form, which is the equation ax plus by is equal to c. And in that method, we could find the x and the y intercepts. Or you may also remember the slope-intercept form, which is y is equal to mx plus b. And there we can use the y-intercept and the slope to get the graph of the line. So what is a system of linear equations? A system of linear equations is a set of two or more linear equations that must be solved simultaneously. This means that we must find the ordered pair that satisfies all of the equations in the system. Graphically, it means that we must find the common point to the graphs of each equation in the system, or in other words, we find the point of intersection. So in this section, we are going to determine if a point is a solution to a system, solve linear equations by graphing, solve special systems by graphing, identify special systems without graphing, and use a graphing calculator to solve a linear system. So let's take a look at our first objective, that is to determine if a point is a solution to a system. We can do this without having to graph, we can just do it algebraically. If we want to know is 2, -3 a solution to the system, then what our criteria was is that it has to satisfy each equation, which means that it has to make each equation true when we plug it in. So if we plug in 2 for the value of x and -3 for the value of y, in our first equation we would get 2 plus -3. Does that equal to -1? And 2 plus -3 is -1, so that does satisfy that equation. In the second equation we plug in is 2 times 2 plus 5 times -3. Is that equal to 19? Well, 2 plus 2 is 4. 5 times -3 is -15. But 4 minus 15 equals -11, not 19. So since it only satisfies one of the equations in the system, we say that 2 -3 is not a solution to the system. Okay? Now what about is -9, -2 a solution to the system? 2x minus 5y equals -8, and 3x plus 6y equals -39. To determine that, we plug the -9 in for x and the -2 in for y. So we would have 2 times -9 minus 5 times -2. Is this equal to -8? Well, 2 times -9 is -18. -5 times -2 is plus 10. And -18 plus 10 is -8, so it satisfies that first equation. If we plug in the same order pair into the second equation, we get 3 times -9 plus 6 times -2. Is this equal to -39? So 3 times -9 is -27. 6 times -2 is -12. And -27 minus 12 is -39. So here we have a point that satisfies both equations, so we say that -9, -2 is a solution to this system. Okay? Now, let's look at actually the method of solving by graphing. That is, given a system, how do we find that point of intersection? So if we want to solve the system x minus y equals 2 and x plus y equals 6, we need to graph both equations in our system. And we can do that with one of two methods. We can either find the x and y intercepts, or we can write each in the slope-intercept form and use the slope and the y-intercept to graph. Or I guess there's another way. You can make a table of values ordered pairs by plugging in x and solving for y until you get at least 3 points to graph. But x, y intercepts are the most common probably if it's in the standard form. So if we were given x minus y is equal to 2, and we need to find the x and the y intercepts, we replace x with 0 and solve for y, and in so doing we get 0 minus y is equal to 2, so negative y is equal to 2, divide by negative 1 to get y is equal to negative 2. Then we would replace y with 0 and solve for x, and in doing that we get x minus 0 is equal to 2, or x equals 2. Now our other equation is x plus y equals 6. We repeat the process. Plug in 0 for x, and notice here if we do that, 0 plus y equals 6, so we just get y is equal to 6. If we plug in 0 for y, we get x plus 0 equals 6, or x is equal to 6. So now what we would do is graph these two lines, and whenever you're graphing to solve a system, you really have to be neat. Use a straight edge. Graph paper would be especially nice because you're trying to identify that exact point that they have in common. So if we plot 0, negative 2, which is on our y-axis, and 2, 0, which is on our x-axis for the first line, and then I'm going to use a straight edge to graph the line that goes through those points. And it's harder to do on a tablet PC, but there was my valiant attempt. And then if we do the second equation, which is 0, 6, so we go up 1, 2, 3, 4, 5, 6, and 6, 0 over 1, 2, 3, 4, 5, 6. Okay. And then if we draw the line between those points, see if I can do that any better. Okay. Then what we would want to do is find the point that they have in common. And it looks like, I think if I was really, really neat, this point 4, 2. And you can see where neatness plays a role. So if I want to check, is the point 4, 2 the solution to this system, I have to plug it in. So we say, is 4 minus 2 equal to 2? Yes. Is 4 plus 2 equal to 6? Yes. So we know that we have solved the equation correctly, and that 4, 2 is our solution to the system. Now notice how these two lines relate to each other. Whenever they cross one another, they're never going to cross a point again on either of the lines because of the nature of the way lines do. So if there is a unique solution, there's only going to be one unique solution, and that is that one ordered pair. Now, if you wanted to do this in an alternate method, you could have solved both equations for y. Like in that first equation, we get negative y is equal to negative x plus 2, divide by negative 1 to get y is equal to x minus 2. And we know from there that the slope is 1, and the y-intercept is 0, negative 2, which means we start at 0, negative 2 and go up 1 over 1, up 1 over 1. The second equation, if we solve for y, we would subtract x to get negative x plus 6. So our slope is negative 1, and our y-intercept is 0, 6. Now remember, negative 1 is really negative 1 over 1, so we would start at 0, 6 and go down 1 over 1, down 1 over 1, and get the graph of the line. So those are two methods that you can use to graph. Now, the next two examples I'm going to show you are some of our special systems, and these aren't ones that are going to look different from the beginning of the problem. The special systems are ones that either have parallel lines, that is, they never intersect, or lines that coincide, that is, that they are the exact same line. So how would you recognize that? Well, obviously you could graph and that information would come out from there. So let's look at that. This time I'm going to practice using the slope-intercept form, just to review that concept. So if I have x plus 2y is equal to 4, remember what I would do. subtract the x, and then divide by 2. So you get y is equal to negative 1/2 x plus 2. So the slope of this first line is negative 1/2, and the y-intercept is 0, 2. My second equation, 2x plus 4y is equal to 12. I'm going to subtract 2x and then divide through by 4. So y is equal to negative 2 over 4 reduces to negative 1/2 x plus 3. So whenever we graph, we have our starting point of the first line is 0, 2. Remember what negative 1/2 means. It means to go down 1 unit over 2, down 1 unit over 2, down 1 unit over 2. You can continue that as long as you want. And then if we graph, let's see if I can make this one better. And our second line is our y-intercept, I didn't even state that, is 0, 3. And our slope is negative 1/2. So we've applied 0, 3, and go down 1 over 2, down 1 over 2, down 1 over 2. And so graphing these points, what do you notice about the lines? These lines are parallel. So whenever we have parallel lines, remember what we need to answer for our solution. The solution is the point that they have in common. Well, if the lines are parallel, they have no points in common. And so the way we would indicate that is that we would say the solution is the empty set, because there's nothing common to those. Now, is there a way you could have told that? Hopefully, whenever I was solving for y, you noticed something. Do you remember we talked about parallel lines a couple sections ago? Parallel lines are ones that have the same slope, but different y-intercepts. So if you have the same slope and different y-intercepts, you will have the case of parallel lines which have no solution. Now let's look at our next example. If we want to solve 2x minus y is equal to 4, and 4x is equal to 2y plus 8. So I'm going to do this one again with the slope-intercept form. So we'd have negative y, if we subtract 2x, negative 2x plus 4. Divide everything through by negative 1, which changes all the signs to get y is equal to 2x minus 4. So this says our slope is 2, or 2 over 1. Our y-intercept is 0, negative 4. The second equation, 4x equals 2y plus 8. Well, we can isolate y on the right. We could subtract the 8 from both sides, and then divide everything through by 2. So we get, what, 2x minus 4 is equal to y. So y equals mx plus b. M is 2, or 2 over 1. And our y-intercept is 0, negative 4. So did you notice something about these two lines? Our slopes are the same, and our y-intercepts are the same. Everything is the same about these two lines. So whenever we graph, we actually only get one line, which we'll see. So remember how to graph. I have to begin at my y-intercept of 0, negative 4. And my rise over run is up 2 over 1, up 2 over 1. And so whenever I connect these points to get my line, looks like this. My second line would be exactly the same thing, right? 0, negative 4, up 2 over 1. So these are the same line. So whenever we talk about what are the points common, every point on the line is common. So you will either have the case of one point being common, where the two lines intersect, that is, across each other, no points being in common, where they're parallel, or every point being in common where there are the same line. So the same line comes from the same slope and the same y-intercept. Now, we say here there are infinitely many solutions because every point on the line is a solution. But there's a unique way to write it. We write it like this. In solution set, in set builder notation, we say it's a set of all ordered pairs x, y, such that the points lie on one of these lines. Well, since they're the same line, doesn't matter which line we write here. We would just write that 2x minus y is equal to 4. So we're saying all points that satisfy this line are solutions to our system. Okay? Now here's a summary and giving you a little bit more terminology. So the three cases of linear systems in two variables are: you have a consistent system, that's where the two lines intersect. So if this is my x-axis and y-axis, they're going to intersect somewhere. And there's one ordered pair solution, and we know that two lines intersect every time their slopes are different. So if the slopes are different, you know you're going to be in the case of one solution. Inconsistent system is what we call a system that has parallel lines. So there's no solution to the system, and we know that because they have the same slopes but different y-intercepts. And then a system with dependent equations is a system that has the same line, or just one line, they're coinciding. And there's infinitely many solutions. That is, every point on the line is a solution. So we have this when we know we have same slopes and the same y-intercepts. So no solution is written as empty set. The infinitely many is written as a set of x comma y, such that, and then you just write in one of the equations. A consistent system, you're going to write it as whatever that single ordered pair is. And to determine which of the cases that you're in, you can just put both equations in the system in the slope-intercept form and compare the slopes and the y-intercepts, and you would immediately know. Now, let's look at solving special systems without graphing, kind of what we just mentioned, where you can solve them both for y, compare their slopes and the y-intercept. So let's just see what would be the case here. In the first equation there, 3x equals 5 minus y, we can subtract 5 if you want. But then we have 3x minus 5y equals negative 1. So we have to divide everything by negative 1 to get negative 3x plus 5 is equal to y. Our second equation, 6x plus 2y equals 10, we subtract 6x and then divide everything through by 2. So we get y is equal to negative 3x plus 5. Well, notice we have the same slope, the same y-intercept, so which case is this? The one where we say they have dependent equations, but that is where there's infinitely many solutions. That is because these are the same line. Now, infinitely many solutions doesn't really tell me the solution set. The solution set is the set of x, y, such that, then I just write one of those lines. I'm just going to write the second one. That is, this is saying all the ordered pairs that lie on that line. Now, the second example here, if we have 2x minus y is equal to 6, we can subtract the 2x and then divide by negative 1 to get y is equal to positive 2x minus 6. So our slope is 2, the y-intercept is 0, negative 6. In the other equation, 4x minus 2y is equal to 8. We subtract 4x and then divide by negative 2. So we get y is equal to negative 4 divided by negative 2 is positive 2x. 8 divided by negative 2 is minus 4. So we have the slope is 2. Oops. And my y-intercept is 0, negative 4. So this is a case where we have the same slope but different y-intercepts. So which case does that correspond to? Yeah, the inconsistent case where they are parallel lines, or the case where there is no solution. Okay? Now, the last example I want to show you how you can use a graphing calculator to find the solution to a system. You actually have to do some work prior to going to the graphing calculator. Graphing calculator only accepts equations in the form of y equals something. So you need to first solve both equations for y. So you'd have negative 2y is equal to negative x plus 6 dividing by negative 2 gives us y is equal to positive 1/2 x minus 3. The second equation is subtracting x and then dividing by 2. So y is equal to negative 1/2 x plus 1. Now notice 1/2 and negative 1/2, they are different values for their slopes. So this case is the case where they are intersecting and we have one unique solution. So what we would have to do to graph this, let's see if I can pull this over a little bit to see my lines for a second. Okay, let me do this. The first thing that we want to do is press turn it on obviously and press y equals, and then you're going to enter 1/2 x minus 3. So 1/2 is our coefficient, so we just enter that as 1 divided by 2x minus 3. Now if you have a TI-82, which I hope none of you do, but if you do, you have to put the 1/2 in parentheses before typing in the x. And then we're going to enter that. And then we need to get our second equation, which was, let's scroll over here, negative 1/2 x plus 1. Okay, so remember the negative from the bottom row, 1 divided by 2x plus 1. Okay? Then we graph. So we see there is a point of intersection. You could use your graphing calculator to kind of read that off on your own, but your graphing calculator has a command built into it where it will actually find the point of intersection for you. And the way to do this is you press second trace, and you see option 5 is intersect. That is the one that will find the intersection of graphs that you have entered. So we can either type in 5 or go down an arrow into it. Then it's going to ask you first curve. That just means I want to be sure which two equations you've entered are the ones I need to find the point of intersection for. If you only have two equations entered, this is really trivial. If you have more than two, you have to think about which two you're trying to find the point of intersection for, and that will come up later in Math 1111. So the first curve is, notice it's in the corner here. Yes, that's our first equation, so I just press enter to say yes, that's my first curve. Then it goes to my second curve. Notice how that changed, and I say yes, that is my second curve. And then guess. The guess means move your cursor left or right to the point of intersection. And then you have to press enter for it to execute the actual point of intersection command. So notice now it says my intersection is 4, negative 1. So I can check. Is 4 minus 2 times negative 1 equal to 6? Yes, because that's 4 plus 2, which is 6. Is 4 plus 2 times negative 1 equal to 2? And that is correct because 4 minus 2 equals 2. So my graphing calculator has given me a way that I can solve this without really having to do any work. Though there's always errors that you can make. You can solve for y incorrectly or things like that. So you really need to always check that point back in the original equations you were given to make sure everything matches up. Okay? So let me copy this for you so that you'll have this in my notes. Okay. So now whenever you go to my notes, you'll see these keystrokes that I entered to be able to get the graph. So I had to press y equals, enter my two equations. Then I had to do second trace 5 to get to the calculate menu. And then I had to enter twice to accept the two curves. Then I moved my cursor to the point of intersection and pressed enter, and that's how I got it to display at the bottom of the screen. Okay? So if you have any questions on any of this, please don't hesitate to contact me. Thank you.